Yes, class. Good evening.
Good evening, ma'am.
So only 3 students have joined till now. Astha, Anushka, and Liana. Let's start with the class because I've already waited for 5 minutes. Now I think we should start. Others will keep on joining. Okay, now we'll start with the next unit. That is your unit number 4 of NCRT. This is unit 4, not 4. First was electrostat, second electrostat. Yes, unit 4. Unit 4 of NCRT. Now this comprises of your EMI and AC. EMI means electromagnetic induction. This is your chapter number 6 of NCRT. Then you have AC. AC means alternating current. This is chapter number 7 of NCRT. So you can refer directly some things from NCRT. See, both of these chapters, all the things we'll cover in the class itself. So you don't even need to refer. You can just have a look at at the NCRT book. Otherwise, the maximum things we'll cover in the class itself. Now regarding alternating current, see, alternating current, we'll do it after EMI. First, we'll start with EMI today. Electromagnetic induction basically arised with the fact, see, in chapter 5th or till chapter number 5th, what did we study? We had seen that there was a current carrying wire, and that current carrying wire produced what? It produced magnetic field. That's what we had observed. So current carrying, if current is there, a conductor is there, then current carrying wire produced magnetic field. This was observed by all of us. Current carrying wire, how did it produce magnetic field? What was the magnitude of that magnetic field? All those things we have covered. Magnitude, we have calculated it with Biot-Savart's law. So we have covered all these phenomena. Now see, then a question arose in earlier times that if we reverse certain things in this only, from this column only, if you just reverse certain things, if magnetic field is present, in a conductor, within a conductor, a magnetic field is present. The question was, now by the reverse formula, will it produce current or not? This became the question. Will there be any production of current using magnetic field in the presence of a conductor? So answer was yes to this, and this was done yes through the help of Faraday's certain laws. Faraday's laws were there. Faraday's laws of EMI are there, that we study in the class itself. Faraday conducted certain experiments, and by that he came to the conclusion that yes, if a magnetic field is present within a conductor, it will produce electric field by itself as well. So all these things were proved experimentally. Experiments are there. In brief, experiments we'll study the experiments, but in your exam I have seen the Faraday's experiments coming directly. All these experiments. So I think you just need to focus on the magnitude part, mainly the law and the associated questions with it. The experiment, we'll cover it. We'll cover the experiment along with itself. Now, magnetic flux. The first topic that comes over here is magnetic flux. First, let's understand magnetic flux. That then add one together, you can write it down. See, EMI is a very easy lesson. 2 classes are enough for EMI, though it can happen. A certain portion will be left that we'll complete later on. But EMI is a very short lesson and it's a very scoring lesson from this unit. Because the next chapter is alternating current. Alternating current is not as simple as EMI. So pay attention in EMI, try to learn all the property, all the formula. It's a formula based chapter, to be honest. Very few derivations are there and totally formula based chapter. Fine. Induction is one of the major topics. Magnetic flux, Lenz's law. These 3 topics are there. 3 to 4. Motional EMF. All these topics. So it's not very difficult for all of you. You'll be able to manage it if you study. Just go and revise it. Your marks also, I'll show it right. Not right now. I'll show it you after the class. I'll send you on WhatsApp after the class. 1 or 2 papers are left. I think Rizan's paper and Liana's paper. 1 or 2 papers are left. I'll check and learn. Okay, Razan and Liana both are here. Anushka, Asthaz, I have sent. I'll send you the marks. Yesterday also some marks of the batches I have sent on WhatsApp. Now also I'll send yours. Yours were left, weekend batch. Let's start with magnetic flux. See, first let me tell you what is meant by electric flux. Electric flux means what? Electric flux simply means when you have a certain number of field lines that are crossing per unit area. Now, what kinds of field lines are those? Those are electric field lines. You have electric field lines that are crossing certain area. For example, this is a plane sheet and a magnetic field line is passing through this and making an angle of 90 degree over this. So I'll say this is the electric flux. If somebody asks me what is the electric flux, I'll say 1 because first only one number of electric line has passed. Similarly, if you bring that concept into magnetic flux, so magnetic flux becomes number of magnetic field lines that are crossing area normally. So number of magnetic field lines that are crossing an area normally are referred to as what? Magnetic flux. Number of magnetic field lines. For example, if I have over here, these lines are at the plane of the sheet making an angle of 90 degree. This is the plane of the sheet. This is making an angle of 90 degree. This is the plane of the sheet. This is making an angle of 90 degree. These are what? These are magnetic field lines. Now these magnetic field lines, these are making an angle of 90 degree. So if somebody asks you, what is the magnetic flux? What should be your reply? What is the answer to this magnetic flux according to the definition that we have just studied?
Ma'am, number of magnetic lines
Yes.
passing through a plane.
Exactly. So how many number of field lines are passing?
3.
3. Exactly. So good. Razan is also right. Yes. 3 class. Exactly. Number of field lines you have to focus. Formula and the rest of the things we'll see later on. Formula and how to calculate everything that we'll study. But practically, if you see the definition of this, definition said this only, the number of magnetic field line that was crossing an area normally. So here also, if 5 magnetic field lines are crossing an area normally, we'll say this is the magnetic flux. Right now, what did we do? Right now, it was magnetic field lines that were present were 3. So if somebody asks you what is the magnetic flux, it will be simply 3. Now, when we reach this part of our first book, then we realize that there are 2 magnetic flux. One was already electric flux. Second one is your magnetic flux. So now if magnetic flux is present, we have to distinguish by some means. So we put a B in the subscript just to denote that this is the magnetic flux. Right? The rest of the definitions and everything that is remaining exactly the same. All right. So this is what number of field lines crossing area normally. This is done. Now let's write the formula part. Because like this, obviously, how many number of field lines will you be able to calculate? If at a particular point there are n number of field lines or a larger number of field lines, so you cannot do actual counting over there to find out the number of field lines. So at that moment of time, what will you do? You have to have a formula, a certain definite formula should be present for the calculation of anything. So same thing will happen over here. Same thing. The formula based, it is This is a plain sheet. Fine. Surface area of this sheet is A. B is the magnetic field. E is the presence of magnetic field. Let's say this is the magnetic field. Magnetic field lines or magnetic field, you can say. Now, n cap is the area vector. Area vector means any perpendicular dropped on the surface of a plane surface. For example, if I say this is a plane surface. If I drop a perpendicular to its surface like this, see, like this. This is known as area vector. A normal to the plane surface, perpendicular line. So perpendicular is area vector. We represent it through n cap. So B is magnetic field, area vector is n cap, and the angle between magnetic field and area vector is theta. This is very important. Angle is very important because most of the students confused with the angle. Sometimes it will be given that the angle between magnetic field and the plane of the sheet is given. That is not your area. Then you will subtract it from 90 degree to obtain this. You should be just concerned with the fact that what is the angle between the magnetic field and the area vector. Only that part you have to consider. This whole will definitely be 90. If something is given you at this point, then subtract it from 90 to get this angle. And formula for phi is this is B dot S. Dot product of magnetic field and surface area. So you can write it as magnitude of magnetic field, magnitude of surface area, BS cos theta. This also you can write. It's a scalar quantity, no need of direction. And one thing regarding the SI unit is Weber. It's Tesla meter square as well, but Weber is also used, or you can write Tesla meter square. Fine. Tesla for magnetic field, meter square for the surface area. Tell me one thing, class. Is it clear till here? Magnetic flux? Clear?
Ma'am?
Yes, Asta.
Ma'am, instead of S, can we use A for surface area?
Yes, say take A if you're comfortable with A, because it happens in schools you are habituated for using A, so you can use A anything, but area should be considered. Fine. So it's not about the variables, because for area you don't have a specific variable. Like magnetic field is denoted by capital B, so you have to use B. Phi is denoted by this symbol. Flux is denoted by this symbol phi, this Greek letter. But surface area has no. So you can write A, B, C, D up to whatever you wish. Okay, class. Note it down, then we'll do numerical. This was a very short topic, magnetic flux. Unit ये मत लिखो. Started from here. Done?
Yes, ma'am.
So this question says that when a magnetic field of 2 Tesla in space, okay, see, magnetic field is what? Magnetic field is 2 Tesla, is inclined at 30 degree with the plane. It means this is the plane and the angle between magnetic field and this plane, this is 30 degrees. Tesla, calculate the magnetic field. If area, see, area is given as 10 meter square. Angle that we have to choose, first we have to drop a normal and subtract 90 to get this. This is 60 degrees, so we'll use 60 degree. Phi will be BA cos theta. So phi will be B is 2, area is 10, cos 60 degree. That will give it, that will become 10 only. Understood why are we choosing 60 degree and not 30 degree? While 30 degree is only provided in the question. The reason is simple, because that 30 degree is formed with this. We want this angle. So we'll subtract 90 degree and we'll obtain this 60 degree. Though the diagram is actually incorrect. 60 degree is looking less and 30 degrees is becoming more. So when you draw it properly. Note it down. One more question on magnetic flux we'll do. Then we'll close this topic and come to Faraday's experiments. Any doubts you people have, please let me know. I'll clarify it. Ask me if you have any doubts.
Ma'am, can you explain this question again? I didn't understand.
Yes. See, magnetic field exists in space. It is inclined at an angle of 30 degree with the plane. It means this is a plane sheet. This is like it's like a plane sheet, and this is the magnetic field. So magnetic field line is inclined at this angle, and this angle is what? This angle is 30 degrees. Fine, this angle. So this angle is 30 degrees. We do not require this angle. We need some angle that is present in within this as well. Fine. So this is what, this is your plane sheet and this is a magnetic field. Now magnetic field is making an angle of 30 degree with the plane. What did I tell you? You have to choose a perpendicular as well. See, if you take a perpendicular to this, that gives you area vector. Forget the magnetic field. If you drop a perpendicular to any of it, surface, any part, that gives you area vector. And magnetic field was making an angle of 30 degree with this. What angle we require? We require this angle between magnetic field and area vector. Area vector is this complete angle, this angle with this blue pen. If you see, this is 90 degree and this part is 30 degree only. So how will you obtain this? This will be 90 minus 30, that will give you 60. Got it? So here only it is simply like this. Magnetic field is present, which is making an angle of 30 degree with the plane. 30 degree with the plane. So if you need the angle between magnetic field and area vector, you will have to subtract it from 90 to obtain this 60. Now is it clear?
Yes, ma'am, here.
See, this question says what? Now it's in Cartesian form. Earlier was in case of polar form when you had the angle between the two vectors. Now the magnetic field is given in terms of Cartesian form. So this is how much magnetic field is given to you as 10 I cap plus 3 j cap plus k cap. All right. It is asking us to calculate the flux through an area 2 meter square in YZ plane. Now, no unit vector is there, so without the help of unit vector, how will we be able to solve both of these? We know phi is equal to b dot a, but even for taking the dot product of two Cartesian vectors, we have to have a unit vector here as well. So unit vector is not directly given, but it is indirectly mentioned that xy plane. So if the sheet is an xy plane, can anyone tell me where the area vector will point? Anybody from all of you? Asma. If the plane surface is in YZ plane, where will the perpendicular or area vector be pointing to? Correct answer, Liana. Good. Anybody else? It's x-axis. See, perpendicular to y. Area vector is what? Area vector is simply a perpendicular. So if this is kept in YZ plane, YZ plane is this? YZ plane. Perpendicular to this will point in which axis? X-axis. So unit vector here will be I cap. So B dot A means 10 I cap plus 3 J cap plus K cap dot 2 I cap. So this will give you 10 I cap into 2 I cap, that is 20. And there are no coefficients, so this will be your answer, 20 pebbles. Got it? See, this is why is this I cap first? Tell me, is this clear to all of you? Why are we writing I cap? Or should I repeat it once more?
Ma'am, I didn't understand.
Okay, Anushka, see. Anushka, if YZ plane, I hope you understand all the planes.
Yes, ma'am.
Okay. Now see, YZ plane is there. This is your YZ plane. Y axis is there. Z axis is there. A perpendicular to all the three axes. See, remember one thing, all of you, that all these three axes are perpendicular to each other. This is the case when we draw the axis. Y, X, Z. All these three are perpendicular to each other. So if Y, Z are present in space like this, Y axis and Z axis are there, something is kept here. Perpendicular to it will point where? To this X axis. So perpendicular to this will give you the area vector's direction along x-axis. So that's why we write here I cap. Because if had it been, let's say, the question would have said in ZX plane. ZX plane would have been this ZX. So perpendicular to this will give you y cap, y-axis, j cap. Had it been saying xy plane, so xy plane, perpendicular to xy plane is what? Your z-axis, so you would have used k. Now understood?
Yes, ma'am, understood.
Oh. Only Anushka clarifies her doubt. If anybody else also has any doubt, let me know. Or just you can even type it in the chat box as well. Note this down, just text me done. Then we'll start with the Faraday's experiment. So magnetic flux was this much only. Done?
Yes, ma'am.
Yes, ma'am.
What about others? Razan, Rayan? Okay, if you all have completed, let's start with Faraday's experiment. Okay, good. Start with the experiment. See, experiments, you just have to see it in brief because experiments writing part usually does not come. So even if it comes, you can explain. So just understand it once. Mainly the first experiment you have to see. Faraday's experiments are very easy. See, I'll tell you. In the first experiment, what happened? He took a coil and rolled it in the form of a circular loop. Fine. And then he connected this loop to a galvanometer. Now he did what? He brought a magnet, bar magnet. Bar magnet we have already covered and the properties of it. So this side is north, this side is south pole, and with any polarity he brought it with, let's say, with some V velocity. What happened? Magnetic field lines were present. But what was observed, not only as soon as the magnetic field lines came, and the number of magnetic field lines got variable, number of magnetic field lines was changing as you bring the bar magnet closer or further away. There was a deflection shown in the galvanometer. What does a galvanometer do? When we were doing magnetics, we had done this also, current sensitivities topic when we were discussing. We had discussed this fact that galvanometer is a device used to detect current. Fine, it's a device used to detect current. So if magnetic field is present, conductor is present, magnet is moving, and galvanometer is getting deflected. So that gives you what idea? It means current is present in the circuit. That's why it is showing any deflection. That was the first thing that was seen. Second thing that was observed was same coil was taken, was looped, galvanometer was there, and this time the bar magnet, north south, this was moved away, some V velocity. It was moved away. Magnetic field lines got decreased. Here, see here, when the bar magnet moved towards it, magnetic field lines increased and the magnetic flux increased. Here, magnetic field lines decreased, flux decreased, but the galvanometer again deflected, but in opposite direction, and it showed deflection. It means still current was flowing. Then to confirm this fact, no, he did one more thing. This is the first experiment only. He didn't move this. Bar magnet. He didn't move the bar magnet. This is north-south. V is equal to 0. He didn't move it. He observed there was no deflection in the galvanometer. It means as soon as it was stopped, there wasn't any deflection in the galvanometer. First experiment clear? So as the magnetic field increased, flux increased. When the flux increased, the current also, it was looking as if it is increasing. When flux got decreased, magnetic field got decreased, current was also decreasing. Then experiment second says that, see, experiment second was here in this experiment, Faraday moved the coil. In the earlier first experiment, what had happened? Coil was stationary, bar magnet was moving. The bar magnet was moving. Now what is happening? Now the bar magnet is kept stationary, the coil is moving. Deflection in the galvanometer was still observed. Then a third case we'll see when we'll do AC transformers. That time you will understand it better. Transformer we haven't done, and transformers we'll not do in this lesson as well. Transformers we'll do it in alternating current. So that time you'll be able to understand this better. See, here what did he do? On a soft iron rod, he wrapped up a primary wire, a wire which he named it as secondary. Then he wrapped it at the secondary and connected it to the galvanometer, and a whole setup was done. So when the current, it was just noted that when the flux magnetic field increased at this part, or the flux increased, a current induced here, because galvanometer showed deflection. No need to go into the details of this third experiment. Nobody is going to ask you. So we'll do this in AC. Remember, when you will do AC, this whole phenomena of transformers will become clear. Fine, these three experiments were done by Faraday. Now, what is the conclusion? Firstly, let me tell you over here. Magnetic field is changing, magnetic flux is changing. If magnetic field is increasing, magnetic flux is increasing. When this happens, when all this phenomena are happening, then an EMF is there in the circuit, as well as a current is also there in the circuit. Current as well as EMF. Fine. Since this EMF is generated because of the movement of magnet, or this is a self-production, no, you are inducing this EMF. There is one EMF that is already present. Since this is present because of the change in flux, so you call this as induced EMF or induced current. Understood this fact? Induced EMF or induced current. This means EMF that is generated because of change in flux. Magnetic field increased, flux increased, induced EMF got present in the circuit. Magnetic field decreased, flux decreased, still EMF got induced in the circuit, induced EMF or induced current. This showed that it's not the increment or decrement precisely. It's just the change in magnetic flux. Now see all the two conclusion points that I had written. If you have not understood, tell me freely, I'll explain it again, because this is a very important part. But this is easy because the experiments are not in detail. Otherwise, the experiments have a lot of detail. Conclusion says, whenever the magnetic flux linked with a closed circuit changes, an induced, here it says an induced EMF and an induced current is set up in it. First, tell me, this first point, is this clear to all of you? EMF and current are there in the circuit. No, EMF and current, it is already present. Now, since it is artificially produced, or you can simply say this is because of the induction or the production of the motion of the magnet. That's why just a name induced has been given. Otherwise, rest of the phenomena of current, rest of the properties of EMF, all these remain the same here. First, tell me, is this line clear to all of you that whenever magnetic flux changes, induced current and induced EMF is present? Clear?
Yes, ma'am.
Yes, ma'am.
Okay. It says that higher the rate of magnetic flux with closed circuit, greater is the induced EMF. This line gives you which hint? If magnetic flux is more, means production, rate of magnetic flux means change of magnetic flux with respect to time. Whatever magnetic flux is changing with respect to time, rate means this only, anything that is getting divided by time. So if rate is higher or greater, higher the rate of magnetic flux, higher is the induced EMF. EMF is high. It means if the rate of magnetic flux is lower, then lesser the induced EMF. So this tells us what fact? This tells us that the magnitude of EMF is directly proportional to the rate of magnetic flux. Then only, no, it is depending upon this. Otherwise, if the magnitude of induced EMF was not proportional to magnetic flux, there wouldn't have been such a direct relation. This relation is proving you the fact that yes, induced EMF's magnitude is directly proportional to rate of magnetic flux within the closed circuit. Got it? From here you get the laws of EMI. This is basically, you just combine this and you write the laws of EMI. See, this is actually a very core and important part. Easy to understand, but important. Do mark it as important. Whenever magnetic flux linked with the coil changes, an EMF is induced in it. This is the first point. Whenever magnetic flux linked with the coil changes, an EMF is induced in it. which is directly proportional to the rate of change of magnetic flux. It means I can write EMF directly proportional to rate of change of magnetic flux. Now, rate of change of magnetic flux, before we directly jump onto this, let's write it in this manner. Let's understand it in a little more detail than what we are studying. Rate of change of magnetic flux means whatever is the change in magnetic flux with respect to time. If I say phi I, this is the initial magnetic flux. This is the final. So change will be what? How do you get the change between any two quantities? So you subtract the final with the initial, that gives you the change. So here also change in flux will be phi F minus phi I, right? Now rate of change in magnetic flux will be d phi, this is your phi, over dt. This is the change in flux, rate of change of flux. Any quantity that gets divided by time or changes with respect to time, you call it as flux. Got it? Now, here we can conclude EMF is what? EMF is directly proportional to d phi over dt. EMF, this is minus d phi over dt. We simply write this because whatever is the constant here is 1. Experimentally, that has been calculated. Now, I had added a negative sign. I have added a negative sign. There wasn't any negative sign. So this negative sign we'll deal later on. This is given by Lenz's law, a very, very important law that we'll see later on. Now, if resistance is given, somehow if resistance is given to me, so induced current, if I want to calculate, how will I get it? See, current is what? From Ohm's law, if you see, E is equal to, V is equal to IRV, right? So if I want to get I will be equal to EMF divided by resistance. And what is EMF? Minus d phi over dt. So here you will get 1 by R. Here you will have 1 by R. Why? See class, this is induced EMF. So this will be minus 1 by R d phi over dt. What did we do? V divided by R, EMF divided by resistance. One last relation we'll see, then you can note it down and clarify all your doubts that you have. Charge is given to you and you have to find out what? You have to find out the EMF. So charge is what? dq over dt. This is equal to current. And what did we write? Current just now. Just now we have written dq over dt and current was written as d phi over dt by R. So from here dt gets cancelled, value of dq comes out to be d phi divided by resistance. So the maximum of the question is difficult, then only this will be asked. Usually E is equal to minus, this can be easily given. So first is E is equal to minus d phi over dt. Then you have value of current. Then you have in terms of value of charge. Main formula is what? Main formula is E is equal to minus d phi over dt. How to calculate d phi? Or even you can not necessarily write d phi. You can write it as minus delta phi over delta t. This just the difference we all know. This is instantaneous. This is average. Tell me all of you, is it clear to all of you? Astha, Anushka, Lian, Razan, Ryan?
Yes, ma'am.
Yes, ma'am, clear.
Both of you, Ryan and Razan? Razan. Clear, okay. Okay. So note it down while writing. If you have any difficulties and queries, let me know. Note down all this. Let me zoom it out. Any difficulties in this? Ask, clarify your doubts. And no need to write down the experiments in detail.
Ma'am, ma'am, I have a doubt.
Yes, Anushka, say.
Yes, ma'am. Ma'am, like in the first experiment, when V was equal to 0, then in that case, the magnetic field, the flux, and the current, all three of them will be zero as well, right?
Yes, because there wasn't any change in magnetic flux. This change that is occurring, no, magnetic flux increasing, magnetic flux decreasing, that led to the EMF. That's why we are constantly referring, and the Faraday's laws of EMI are also emphasizing on this fact that the change in magnetic flux, when the magnetic this your bar magnetic is at rest, then there is no change in the magnetic flux. See, magnetic field will be there because magnet is there, so magnetic field will be there, but there is no production of induced EMF or induced current because there is no change in the magnetic flux. Magnetic flux is there, but its value is constant, it's not changing. Understood?
Yes, ma'am. Ma'am, could you scroll up for a second to the experiment field diagram?
Yes, Anushka?
Ma'am, can you scroll up to the experiment
Yes,
field?
yes, yes, yes.
Yes, ma'am.
Written class.
Yes, ma'am.
Okay, so 2 questions are there in this topic before we start with lens flow. So that we'll do tomorrow only because not much time is left. Class tomorrow we'll be having a class of 2 hours duration. Just tell me, do you have any class half an hour later as well tomorrow? After this, like if I extend it to, for me it will be till 8:30. Then for you all it will be how much? 6 o'clock.
Ma'am, for me it will be 7.
4 o'clock.
7.
Okay, 7 o'clock. So yes, if you all are available, just let me know because your class duration has to increase now. But no, I'm not increasing it continuously. I am increasing it for just tomorrow. So at least we can complete a major portion of this lesson, EMI. So that next week we can start with alternating current. So 2 hours duration class will be like we'll take a break also in between when 1 hour will get completed. I'll give you a break as well of 5 to 10 minutes. Then let's complete the major part of this. So right now you all can leave. Thank you so much. Any doubts you have, let me know. I'll share your.
Ma'am,
Yes, Niana.
ma'am, tomorrow maybe I might have to leave a bit early.